Let me tell you something that took me years to really understand, and when I finally did, it changed everything about how I see the universe. You ready? Here's the question. If you're running at 99.9% the speed of light, and you turn on a flashlight, does the light travel faster than light? I mean, you'd think so, right? You're already going almost as fast as light, and now you're adding light's speed on top of that. Should be faster than light. Has to be faster than light. Except it isn't. That answer, that simple little no, contains one of the most profound truths about reality that we've ever discovered. And when you understand why the answer is no, you'll never look at space or time the same way again. You see, I spent a lot of my life thinking about how things move. At Los Alamos, at Caltech, in my head while I was supposed to be doing something else. And the thing about motion is, we think we understand it because we've been watching things move our whole lives. You throw a ball from a moving car, you add the speeds. The car's going 30 miles an hour, you throw the ball at 20 miles an hour in the same direction. Someone standing on the sidewalk sees the ball going 50 miles an hour. Simple arithmetic. 5-year-olds can do it. But here's the thing. That simple arithmetic, it's wrong. It's approximately right for slow things like cars and balls and airplanes, but it's wrong. And when you get to speeds that are a significant fraction of light speed, that wrongness becomes impossible to ignore. Let me explain how I started thinking about this. When I was younger, I read about Einstein's special relativity, and like everyone else, I thought, well, that's very clever, but it seems kind of arbitrary. Why should light be special? It bothered me. I don't like accepting things just because someone says so, even if that someone is Einstein. I wanted to understand why. So I started thinking about it the way I think about most things. What do we actually know? What can we actually measure? And what happens if we take those measurements seriously, even when they tell us something we don't expect? Here's what we know. Every time we measure the speed of light, we get the same answer. Doesn't matter if we're moving toward the light source or away from it. Doesn't matter if the light source is moving toward us or away from us. We measure about 300 million meters per second. Always. Every single time. Now, at first, this seems crazy. If I'm running toward a light source, shouldn't the light look faster to me? That's how it works with everything else. If I'm running toward a baseball that someone throws at me, the baseball approaches me faster than if I'm standing still. That's just common sense. But common sense is just the collection of prejudices we've acquired by age 18. And in this case, common sense is completely wrong about light. The experiments don't lie. Michelson and Morley did this beautiful experiment back in the 1880 seconds. They were trying to detect the motion of the Earth through space by measuring the speed of light in different directions. They figured if the Earth is moving, then light going in the same direction as the Earth should seem slower, and light going the opposite direction should seem faster. Makes perfect sense, right? Except they found nothing. The speed of light was exactly the same in every direction. At first, everyone thought there must be something wrong with the experiment, so they did it again and again with better equipment. Over decades, same result. The speed of light is constant, period. Now here's where it gets interesting. Einstein was the one who finally said, what if we just believe the experiments? What if the speed of light really is the same for everyone, no matter how they're moving? And then he asked the obvious question, what does that mean? Let me show you why this leads to something mind-bending. Imagine you're in a spaceship going 90% the speed of light. You turn on a flashlight pointing forward. Now, you measure the speed of that light beam. What do you get? 300 million meters per second, normal light speed. Nothing unusual from your perspective. But wait, I'm standing on Earth watching you fly by. I see you going 90% of light speed. I see your flashlight beam going forward. So how fast does that beam appear to be going from my perspective? If speed's added normally, I should see the light going 190% of light speed. But we just said the speed of light is the same for everyone. So I also measure that light going at 300 million meters per second. You measure 300 million. I measure 300 million. But you're moving at 90% of that relative to me. How can this possibly work? This is where people usually say, that's impossible. The math doesn't work out. And they're right that something strange is going on. But here's the thing, it does work out. The math does work. It's just that something we thought was fixed and absolute turns out to be flexible. What's flexible? Time and space. You see, we always assume that 1 second is 1 second, no matter where you are or how fast you're moving. We assume that 1 meter is 1 meter. These seem like such obvious truths that nobody questioned them for thousands of years. But if you demand that the speed of light be the same for everyone, you have to give up on those assumptions. Time has to run at different rates for different observers. Space has to contract. There's no other way to make the math work. Let me put it more concretely. When I watch you fly by at 90% the speed of light, your clocks appear to run slow. Not because there's something wrong with your clocks. Not because of some mechanical effect. Time itself, actual real time, is passing more slowly for you relative to me. And here's the really strange part. From your perspective on the ship, you're stationary. It's me on Earth who's moving past you at 90% of light speed. So, from your perspective, my clocks are running slow. This seems like a contradiction, right? We can't both have slower clocks than the other. But actually we can, because we're not comparing our clocks directly. We're comparing them from our different perspectives, and those perspectives are equally valid. This is what Einstein meant by relativity. There's no absolute frame of reference. There's no cosmic stopwatch that tells you what the real time is. Every observer's measurements are equally valid, and they all have to be consistent with the speed of light being constant. Now let me explain why speeds don't add up the way we expect. When you add velocities, you can't just add them arithmetically. There's a formula that takes into account the fact that the speed of light is a limit. When both speeds are much smaller than light, the formula gives you almost exactly the simple addition we're used to. But as speeds get higher, the formula bends things so that the total never exceeds the speed of light. Here's the formula in words, because it's actually quite beautiful. When you add two velocities, you add them the normal way, but then you divide by 1 plus the product of the two speeds, divided by the speed of light squared. When speeds are small, that divisor is essentially 1. So you get normal addition. But when speeds get close to light speed, that divisor gets bigger, and it pushes the result back down below light speed. So if you're going 90% of light speed and you turn on a flashlight, the light is not going 190% of light speed relative to the outside observer. The formula tells you that it's going about 99.4% of light speed, still less than light, always less than light. No matter what you do, no matter how you move, no matter what reference frame you're in, light always moves at exactly light speed relative to you. But here's the question everyone asks. What happens if you try to actually go at light speed? Can you do it? The answer is no, and the reason is beautiful and terrible at the same time. As you accelerate toward the speed of light, something happens to your mass. Now, when I say mass, I have to be a little careful. There's a concept called relativistic mass that increases as you speed up. Some physicists don't like that terminology, but the effect is real regardless of what you call it. The energy required to accelerate you increases. Here's the thing. To accelerate something, you need energy. The more massive it is, the more energy you need. As you approach the speed of light, the energy required to accelerate you further increases without bound. It goes to infinity. Let me say that again. To actually reach the speed of light, you would need infinite energy, not a lot of energy, not more energy than exists on Earth. Infinite energy, which is to say, it's impossible, not just hard, not just impractical, fundamentally, physically, mathematically impossible. This is why nothing with mass can ever travel at the speed of light. The faster you go, the more energy it takes to go even faster. As you approach light speed, that energy requirement approaches infinity. You can get closer and closer to light speed, 99%, 99.9%, 99.999%, but you can never actually reach it. Photons, light particles, travel at light speed because they have no mass. They have energy, they have momentum, but they don't have rest mass. They're born traveling at light speed, and they never slow down until they're absorbed by something. But anything with mass is trapped below that barrier forever. Now, here's a consequence that will really bend your mind. Time dilation has been measured. We've done the experiments, we've put atomic clocks on airplanes and flown them around the world. When they came back, they disagreed with clocks that stayed on the ground. By exactly the amount relativity predicted. We've seen particles called muons in cosmic rays. Muons are unstable. They decay in about 2 microseconds. They're created in the upper atmosphere when cosmic rays hit air molecules. The thing is, the upper atmosphere is about 30 kilometers up. Even traveling at nearly the speed of light, muons should only be able to travel about 600 meters before decaying. They shouldn't be able to reach the ground. But they do reach the ground. We detect them at the surface. How? Time dilation. From our perspective, the muons' internal clocks are running slow because they're traveling so fast. Their 2 microseconds of lifetime is stretched out. From our perspective, they live long enough to reach the ground. And here's the really mind-bending part. From the muon's perspective, it still only lives 2 microseconds. But from its perspective, the atmosphere is length contracted. The 30 kilometers has shrunk to about 600 meters. So the muon doesn't have to live longer. The distance has gotten shorter. Both perspectives are correct. Both descriptions are valid. That's the nature of relativity. So now we come to the big question. Why? Why is the speed of light the limit? Why did the universe work out this way? I've thought about this a lot, and here's what I've come to understand. The speed of light isn't really about light. Light just happens to travel at that speed because it has no mass. The speed we call c is actually the speed of causality. It's the fastest that any cause can propagate to create an effect. Think about it. If you could send a signal faster than light, you could, in principle, send information backward in time. The mathematics of special relativity show this clearly. Faster than light travel would mean time travel, and time travel creates paradoxes that seem to violate basic logic. So the speed limit isn't just some arbitrary restriction, it's what keeps cause and effect in their proper order. It's what keeps the universe making sense. Now, does that mean nothing can ever go faster than light? Well, the expansion of space itself can carry galaxies away from us faster than light. But that's not the same as something moving through space faster than light. Space itself is stretching. The galaxies aren't violating causality because they're not communicating with us. They're just getting farther away because the space between us is expanding. Also, there are ideas about warp drives and wormholes that might, in principle, let you effectively travel faster than light by manipulating space-time itself, but these are speculative. We don't know if they're possible, and even if they were, they wouldn't violate the fundamental principle. Nothing moves through space faster than light. What really gets me, though, is how this all fits together. The universe has this beautiful, elegant structure. Time and space are not separate things, but aspects of one thing, space-time. Mass and energy are not separate things, but aspects of one thing. And this speed limit, this cosmic speed limit, is what ties it all together. When I first really understood this, when I stopped just knowing the formulas and started seeing the picture, it changed how I thought about everything. The universe isn't a stage where things happen. The universe is the things that happen. Time isn't ticking away in the background. Time is part of the geometry of reality. And here's the final thought I'll leave you with. We live our entire lives in a tiny corner of reality where nothing moves very fast. We never experience time dilation. We never notice length contraction. So our intuitions, our common sense, is built for a slow, small world. But the universe doesn't care about our intuitions. The universe does what it does. And what it does is far stranger and more beautiful than we ever imagined. That's what makes physics wonderful. Not that it confirms what we already believe, but that it shows us how wrong our beliefs can be. The speed of light as an absolute limit. Time that stretches and shrinks, space that contracts, mass that increases, it all sounds impossible. But it's not only possible, it's how things actually work. We've measured it, we've tested it, we've used it to build technologies that run our world. Reality doesn't ask our permission to be strange. It just is what it is. And our job, the wonderful job, is to figure out what that is and then sit back and appreciate just how remarkable it all turns out to be.